Hello everyone, guess who is back with yet another linear transformation video. Now before you get too worked up, as the title is suggesting us, we are hoping to have some fun in this video with linear transformation, and I think you are actually kind of going to like this one. So let's hope for the best. I do know, however, that some of you are absolutely furious because you probably think we are teaching you too many theories and too many hard stuff. To be honest, I literally can feel some of you boiling over in front of your screens right now. But I do believe that the things we are teaching you and in the manner we are teaching those, they are absolutely essential for your proper understanding of linear algebra, and these concepts are very important on their own. In your academic career, I'm sure you're going to find these concepts very useful many times. Now, there can obviously be disagreements, but as your instructor, I'm going to use this video to try to convince you these are actually worth our time. So let's begin. First of all, obviously, linear transformation is necessary for understanding linear algebra. Your understanding of vector spaces and system of linear equations are going to be incomplete without your understanding of linear transformation. We have already seen matrices as a tool for storing data. We have seen matrices as linear transformations, how matrices cause a space to transform, and that's not where the interpretation ends. In the future, when you're going to study linear equations and system of linear equations, you will see that a matrix can answer every possible question you might have about a linear equation. But all of these are part of our course, so you are going to study those anyway, and I'm not going to get into that in this video. So let me move on to something else. And that something else is computer imaging and computer graphics, which have built their entire foundation on linear transformation. Let me give you an example. Now see this photo. This is a photo of Taj Mahal I took a couple of years back somewhere in India. Not somewhere in India, obviously this is in Agra. Anyway, so this is a photo of Taj Mahal, right? Now there are many photos of Taj Mahal and all of those don't look exactly the same. Like if someone else took the same photo from a different device, it might have different proportions. And if someone took the same photo from a different position and a different angle, it might have looked like this, or even it might have looked like this. And if someone had a complete different point of view, it could have looked even like this with different perspective. Now all of these photos are of the same thing, but how are you going to tell a computer that? Because the computer cannot see like us, they just analyze pixel by pixel. Now all these variations of the same photo are related by linear transformations, because if you notice, this is just a little bit of rotation and a little bit of scaling from the original photo. This photo has a little bit of parallel skew, and this photo has perspective, which is interesting because if you notice, because the line going along the y-axis are converging somewhere. So the parallel lines that were parallel before the transformation are not parallel anymore, which is a violation of our rule. And that is true. By that logic, this is actually not a linear transformation, and this is called a projective transformation. And when we are using our familiar Cartesian coordinates, this cannot be expressed by a matrix transformation. But there is a different coordinate system called the homogeneous coordinate system, and when you apply that, even projections can become linear transformations. The details of that process is not important for you right now. I just want you to appreciate the fact that things like rotation, skewing, and scaling, and even perspective and translation when you are using a different coordinate system called the homogeneous coordinate system, all of those can be achieved by linear transformation. And that is a huge application for linear transformation because these are being used in computer imaging all the time, literally all the time. Now let's focus a little bit on rotation here, and for that I'll need my blackboard, so let's bring it back. So here is our board, and what we are trying to do is that we are trying to find a matrix that will rotate all the vectors of a plane by a certain degree, let's say theta degree. And we already know that to find that, all we have to do is to find out what happens to our two vectors I hat and j hat, two basis vectors. So let's see. When I hat will rotate a certain degree, let's say theta degree, we have I hat right here. So it has rotated to this position. The degree is called theta, and as I hat is an unit vector, so the length of this is 1, right? So let's draw a right angle triangle. So can you tell me what is this and what is this? Let's bring back. Now this is 90 degrees, this is theta. So if I call this 0 OA, this is OA sine theta, right? But OA is just 1, so this is 1 into sine theta, and the base is 1 into cos theta. So that gives us the first column of the matrix, because the first column is where the I hat is going to be transformed to, and apparently the I hat vector is getting transformed to cos theta sine theta position. So the first cos theta, first column is going to be cos theta sine theta, because the position of this vector is from O to A, and A is cos theta sine theta. So let's see what happens to our J vector. Okay, so this is going to be rotated. Let's bring another color. This is going to be rotated theta degree too, right? And this is theta. This is again 1 because J hat was an unit vector. Do the same thing. So I need to know what this point is, and this point, just like before, is going to be sine theta. The length of this is going to be sine theta, and as this is on the left side, so we have minus sine theta, and the length of this is going to be cos theta, right? And this is on the positive side, so we have cos theta. So as we can see, the matrix for rotating something is cos theta sine theta and and minus sine theta cos theta, right? So this is our matrix. Multiply this with any vector and the vector will be rotated by theta degree. Now let us test the theory. We have our first row, first column here, which is cos theta. First row, second column is minus sine theta. Second row, first column is sine theta, and second row, second column is cos theta. We have a triangle drawn here and I want to rotate it. Now instead of fixing a certain value for theta, I have used a variable x, and the value of x will continue to increase and the rotation will keep happening. So let's see. To help you visualize, I'm going to draw the vectors as well. So this is our A vector, our B and C vector. So what is happening here is I'm rotating these three vectors, and as the position of A, B and C is changing, the position of the triangle is changing as well. So now let me draw the transformed triangle. This red one is our transformed triangle. Right now the value of x is 0, and as there has been a 0 degree rotation, our original triangle and our transformed triangle are sitting on the same place. Let me start changing the value of x right now. You see, I am only multiplying three vectors with a certain matrix, but the result is phenomenal. It's amazing how much can be achieved in computer graphics by using such simple concepts of linear transformation. And if you think this is cool, let me show you the 3D version of it. These are the rotational matrix for the third dimension. One is for rotation around the x-axis, one is for rotation around the y-axis, and of course the third one is rotation around the z-axis. Now these matrices can be determined just the way we determined the rotational matrix for 2 dimension, but the geometry is a little more tricky and I'm not going to go there. So I have already put the values in place for our 3x3 rotational matrix. We are rotating around the z-axis here, and just like before, for the angle I am not using a fixed value, I am using a variable x that will keep increasing. So let's see how it looks. So this is our 3-dimensional object, a pyramid. I want to rotate it around the x-axis. To understand the rotation better, just like before, I'm going to draw the vectors as well. So this is the vector A, this is the vector for point B, this is for point C, and this is for point D. Now currently the value of x is 0. So if I transform our pyramid using the current values, our transform pyramid is just going to sit on the original pyramid because the rotation currently is 0 degree. So now I'm going to increase the value of x to see how the rotation looks like. And voila! So this is our rotation, a three-dimensional rotation just by multiplying 4 points using a matrix. If that's not cool, I don't know what is. Well, I actually know some other cool stuff, but this is cool too. So this is our rotation around the z-axis, right? As you can see, the blue axis here is the z-axis, and the pyramid is rotating around the z-axis. Let me now change the value of the matrices to make it rotate around the x-axis. I actually have already done that. So our matrix is 1 0 0 first row, 0 cos theta minus sin theta second row, 0 sin theta cos theta first row, and as usual our variable angle is x, which is currently at 0 degree. Alright, so let's make it rotate. I'm going to start increasing the value of the angle right now. And as you can see, the pyramid is not rotating around the z-axis anymore. Just by changing the matrix slightly, I have changed the entire rotation. It is now rotating around the red axis, which is the x-axis. Pretty cool, right? You have to admit, come on, it's pretty cool. Before I leave you, I'm going to show you another website where you can play with linear transformations yourself. And the website is this one. We have a 2 by 2 matrix here. You can change the value yourself and do whatever you want with it and see the effect in real time. So let's say I want to rotate the matrix 90 degree, right? So our I hat vector is going to go there. So my first column is going to be 0 1 instead of 1 0, and I want my j hat vector to go from here to here. So from 0 1 it will be -1 0. Press enter and see 90 degree rotation. Let's say I want to let's go back to how it was before. So this is our original picture. Let's say I want to skew it, but not horizontally. I want to skew it vertically. So I will keep my y-axis as it is, but the I hat vector, I'll go from here to here. So this is 1 1 position, right? So I'll just change the this is j hat. I'll just change the first column to 1 1, and here is the skew. You can visit the website and change the values yourself and see how the picture reacts to various changes you bring into the matrix. I'm going to give you the link somewhere in the screen. Just find it yourself. I hope that was at least to some extent interesting, and I promise this is the last video of linear transformation. Next week, not next week, next lecture, we are going to start talking finally about linear equations. Until then, goodbye and see you soon.